solutions and concentrations. Our exam, we had intermolecular forces. We were talking about different molecules and how they interact with other molecules without breaking and forming bonds. And then we also had stoichiometry, which is really just the way that we count whole numbers of things in chemistry, right? How do we get a certain number of products from a certain number of reactants, right? And we talked about the chemical quantity of the mole. And so all of these things are important for chemical reactions. Today we're going to talk about, the actual types of chemical reactions that are relatively common and what they, some examples of those. And we're going to talk about some, specific states of matter and different chemicals or compounds that are pretty common in the study, right? So we'll eventually get into gases, which is important for gas phase reactions, and acids and bases, which is pretty much important for everything because it's so intimately related to water. But before we jump into the different types of chemical reactions, why don't you guys take a second, see if you can balance each of these reactions, right? So balancing reactions is important because it tells us the whole number ratios at which atoms and molecules combine to form products, right? So when we balance a chemical equation, we're just looking at the whole numbers of how many reactants create how many products. And in chemical reactions, right, we're not just looking at the properties, the intermolecular forces between molecules. Now we're looking at something a little bit more complicated where we have bonds breaking and bonds forming to form new compounds and new molecules. And that's what the chemical reaction represents, right? So just to review, we have our products. Our products go on which side of the chemical reaction arrow? Right. We have the right. Yep. We have our products, and then we have our reactants, and our reactants go where? On the left, reactants, and they're separated by an arrow that tells us that represents the chemical change. Right. This is actually a very complicated process where, if we were to go down to the quantum realm, you would see, electrons zipping around, moving from one atom to another and from one molecule to another. But we're just representing it by a chemical reaction, right? Just this symbolic representation of all that going on. And then we can have things like delta, catalysts and stuff, and those represent the different types of reaction conditions that can happen, right? So this was our general diagram. And then in front of each of our reactants and products, we can have our stoichiometric coefficients, right? And that's what we change when we're balancing chemical reactions. Right? And that's what we're actually using to balance, right? We can't change the subscripts because the subscripts are determined by the compound. So if we know what compounds are being used up and what's being produced, then we're not changing the subscripts at all. We're just changing how many of each molecule we have for the chemical reaction to happen. Oops. You guys don't want to see that. So I'll go over the first one real quick and then let you guys keep working on the rest. So like I said, the first thing you'll probably want to balance is the silver here. We have 2 silvers on this side, right? And the only way we can change the number of silvers on the left-hand side is by adding a coefficient 2 in front of the silver nitrate, right? So once we balance the silver, now I'll look to see if sulfur is balanced. Looks like sulfur is balanced. And I'll then check to see if nitrate, right? So nitrate is a polyatomic ion, right? Polyatomic ions, generally we treat them as their own species when balancing chemical reactions. So we have 2 nitrates on this side now and only 1 nitrate on the product side. So what I'm going to do is I'm going to multiply this whole thing by 2 as well. Now the number of nitrates on both sides are balanced for this reaction. And so I'll check hydrogen now. So I know the sulfur is balanced. I know the silver's balanced. I know the nitrate's balanced. The hydrogen is the only thing left. I have 2 on the left side and then 2 on the product side, right? I have 2 here, and then now I have 2 hydrogens there as well. right? So when balancing the polyatomic ions, usually it's easy to treat them as their own species. For the next reaction, so we'll do that one really quick right now too, it's a little more challenging because this polyatomic ion gets changed into the form of water. So that's how that's going to start showing up in this reaction. And it's because the ion exchange is going to be with the hydrogens that are bonded to this compound right here, which is called sulfuric acid, right? So we're still going to do the same thing, balance the metal ions first. That's usually always a good place to start. And then we'll balance the sulfate ion and see if that will then make things a little bit simpler. All right, so if I was to balance the aluminum, how would I balance the aluminum on the reactant side? What would I do? Yeah, we'd have 2 of them here, so we put a 2 there. Now we're balanced on both sides. Then I'm going to look at the sulfate ion, right? So this is, we have how many on the right side?
6. Well, now we have 6.
We have 3, right? Because this parentheses, right? Each sulfate ion, there's 3 of them because you have a 3 on the outside, right? We haven't multiplied this whole thing by 2, right? We multiplied this on this side by 2, but we haven't done anything to this right here. The subscript only talks about the aluminum. If we were to put a 2 here, then we would have 6 of them. Right, so we have 3 on the right side, and then we need 3 on the right side, so what am I gonna do with sulfuric acid? How am I gonna adjust that? This is sulfuric acid.
Well, you'd actually add the 3 on the reaction.
Yeah, we had a 3 here, right? So now also our sulfuric acid, or our sulfate ion, which again, the sulfate ion is SO4, 2 minus, right? That's a polyatomic ion. Now that's balanced on both sides. And so now the last thing I'll look for is the hydrogens, right? And because, I'm assuming that this water is gonna take into account all of the oxygens that are from the hydroxide, because the hydrogens are really only coming from the sulfuric acid. And so the hydrogens on the left side, how many hydrogens do I have total?
6.
We have 6 from sulfuric acid, and then we also have, right, 3 for each aluminum hydroxide. Then we have 2 of those, right? So we have 6 there. Right, so we have a total of 12, right? So we have a total of 12, and then if we look at the oxygens that come from here, right? Because we've already balanced the oxygens that are in the sulfate ion, right? This is why it's a little tricky with the polyatomic ions. We're just looking at balancing the hydrogens right now. We can see that we can balance the oxygens associated with water just by balancing the hydrogens, right? So if we have 12, what do I need to do to the water molecule on this side? Put a 6 in front of it, right? Because if I put a 6 in front of it, then I get 6 times 2 is 12 total hydrogens and 6 oxygens. And if we double check now, we see that the oxygens, each one, we have 3 hydroxides per each of these molecules, 3 oxygens times 2 gives us 6. That's 6 oxygens that are associated with the water, right? So the sulfate kind of handled all of the oxygens that are associated with the sulfur in both of these molecules, and the water is dealing with all the oxygens in the hydroxide, right? So polyatomic ions can be a little tricky. The kind of workaround to this is just you always balance the polyatomic ions like they're their own entity, right? They're their own atom that you're balancing for. Okay, and did anyone do the third one? Anyone finish it? Anyone have coefficients for that yet? What did you get for coefficients?
I got 4 in front of H2.
Okay, 4 in front of H2.
And
3.
4 in front of H2.
Yep, so it looks like we have, if we were to balance the metal first, right, iron, we have 3 on the iron oxide, and then we need 3 on the right-hand side of this equation, so we balance that, that looks good. Then we can start looking at the hydrogens. Well, the hydrogens are originally balanced, so let's look at the oxygens. We know to balance the oxygens on the left-hand side, we have 4 there. We multiply the number of water molecules by 4. That balances the oxygens, but it's also changed the number of hydrogens now. We have 8 there, so we need to make sure we have 8 here. We do that by putting a 4 in front of the hydrogen gas there, or elemental hydrogen. All right, so that looks good. All right, any questions on that one? And the last one, this is a familiar reaction because these are the combustion reactions, right? Combustion reactions, you usually have the same procedure for all of them. Balance the carbon because it only shows up in one molecule on each side, then balance the hydrogen, and then you might have to do a little, massaging of the equation to get the oxygens to balance out, right? And the reason for that is because on this side of the equation, we can have odd numbers of oxygen because we have 1 in this molecule and 2 here, right? So we can add it in weird multiples of odd numbers sometimes. And on this side, it can only be in even numbers. And so I know on the exam, the balancing of the combustion reaction, on office hours on Sunday night, not the exact combustion reaction, but a very similar one. Generally, if you run into something where you see half integers of a coefficient, the trick to deal with that is just to multiply the coefficient by whatever you need to make it either even or divisible by the number you're adding it by. So that's a fancy way of saying if I need the number of oxygens on this side to be even, I can just multiply everything by 2, right? And any odd number times 2 is an even number. Why? Because you made it divisible by 2, which is what's the definition of it being even, right? 3 times 2 is 6, even number. 7 times 2 is 14, even number, right? So that's the way you deal with that. What if it was 03 on this side, right? If it was something that you can only add multiples of 3, then you would multiply the whole equation by 3. And when you did that, now you've made it everything divisible by 3 just by multiplying it, right? So this is kind of the trick whenever you kind of run into that situation. Otherwise, it gets easy to kind of, keep adding and subtracting, and then it's like, okay, I'm going to get, something that's not really solvable. Okay, so for first thing we're going to balance is the carbons, right? So how do I balance the carbons? What do I change the coefficient of? Carbon dioxide, right? We're going to change this, and what am I going to change the coefficient for? We're going to put a 4 there, right? Because we have a 4 here, and we have 1 carbon in the carbon dioxide, right? 1 carbon in the carbon dioxide, so we need 4, so we multiply it by 4, right? And then we're going to look at the hydrogens, and how do I change the hydrogens here? All right, we have how many on the left-hand side, the reactant side? 10, and how many on the product side? 2. So what do I multiply that by? 5, right? So put a 5 here. And now we come to the tricky part of the oxygen. We have how many oxygens on the right-hand side of this equation? We have 4 times 2 is 8, right? 4 times 2 is 8 oxygens from the carbon dioxide. And usually I write the whole table and everything. I don't have a whole lot of space here, so that's why I'm not doing that. And you guys have seen that before. So I'm just focusing on the elements as we're going. So we have 8 oxygens from there, and then we have how many from the waters? 5 plus 5 oxygens, so we have 13 oxygens total, right? 13, right? So this is where the divisible by 2 even number thing comes in, right? Because we can only add oxygen in even amounts here, right? What would 13 divided by 2 be? 6.5, right? So that's the only way that this would work, is if we had half integer. But we're not allowed to have a half integers because, does anyone have a physical reason for why a half integer doesn't work? Yeah, well, anyone have why does it have to be a whole number? Besides me just telling you it has to be. Okay. Yeah, you can't have half a molecule in a reaction, right? That doesn't really make sense to have half a oxygen atom or half of an oxygen molecule, right? When molecules come together, they come together as a whole molecule interacting with another whole molecule. You don't have half an oxygen coming into the system, right? So that's why they have to be whole numbers. That's a physical interpretation. And so if you got to this point, this is fine, right? Now you just have to realize that I can make this all whole by just multiplying everything by 2 as well, right? So you could multiply by 2 before and then balance the oxygen, or I can just take this, all the coefficients, and multiply by 2, and then the coefficients in this order would be 2, 13, 8, 10, right? If this was each spot right here. 2, 13, 8, 10. Those would be the balanced coefficients, right? Because if I multiply everything by 2, 2 times 1 gives me 2, 2 times 6.5 gives me 13, 2 times 4 gives me 8, and 2 times 5 gives me 10. That's where all of those come from.
So you would do it first and then multiply the whole thing?
Yeah, you can put the coefficients first and then multiply it all if you want. The other way that you can do that is if you knew that at this point, H10 plus O2 goes to 4 CO2 plus 5 H2O. If at this point you realized, okay, I have to need to multiply the coefficients by 2, you can put a 2 in front of everything, right? C2 H10 plus O2 goes to 8 CO2 plus 10 H2O. You could do this and then it's balance. Then you just have to find what that has to be. And now you know you have 16 oxygens here plus 10 oxygens, 10 oxygens here, so you have 26. And then I just have to multiply this by 13 to get the 26. All right, so that's the other way you can do it, whichever one makes more sense.
I hope so.
Yeah, so this is for combustion reactions. This is where you kind of see this. There's other reactions where you could see this too, but combustion reactions are one that we deal with a lot in chemistry. Okay?
I have two questions. Whenever we have chemical equations that are similar to the one on the exam,
Mm-hmm.
so whenever you have very high coefficients, how would you like deal with that? Because I was stuck on that problem for like 40 minutes.
Yeah, so that's why the problem is layered that if you got the wrong coefficients, you could still do parts B and C with whatever coefficients you had, right? Because if you got the numbers wrong, you can still say, oh, well, I understand that these need to be balanced. I just can't get the numbers to work out for whatever reason. It's like after a tough loss in, any sports match or game, right? To be able to go on and do the next part, you have to kind of mentally say, okay, whatever, I couldn't get that to work out, but I can still move on with the problem. That's how I would deal with that personally, right?
Yeah, I was like literally about to cheat and just put like a decimal.
Well, yeah, I mean that's not cheating, right? That is the whatever. If you did have a decimal point, actually, your other answers would come out numerically correct, right? So numerically, it still works that you can have that, right? Because if you had 13, let's say your ratio was 13 O2 moles of O2 per, I don't know, 10 moles of H2O. This is something else, right? This ratio is still the same as 6.5 moles of H2 or O2 per 5 moles of H2O. That number itself is actually the same. So you get the same numerical value. But let's say you didn't realize, okay, I have to multiply that by 2 to get the correct coefficients, right? It's I don't know everything in the universe. It's okay not to know everything. I couldn't get that to work out within the time frame of the exam. I'm sure if you guys had enough time, everyone would be able to figure it out. So.
I had just like a very good question. So
Mm-hmm.
you were saying that decimals, they don't necessarily work. We know that oxygen is a diatomic
Mm-hmm.
atom. So whenever we have something like that, if we were to try to hypothetically use a decimal and split it in half in the real
Mm-hmm.
world, would that cause like an explosion?
I mean, that is how energy is released a lot of times, right? If you had a molecule that has a lot of nitrogens and stuff, for example, you break those carbon-nitrogen bonds, and that's what releases a lot of the energy, right? It's all about the movement of electrons. They're going from like a high energy state in a bond to a lower energy state. And when they go to a lower energy state, they release energy, right? That's when we have something that's exo or endothermic. And so the half number ratios, the reason that they don't make sense isn't necessarily because half of that molecule can't ever exist. It's because this chemical reaction is defined with these reactants and these products, right? So if you mixed in, for example, instead of, you mixed in, C5, H10, or C2, C4, C4H10 plus just, an oxygen atom for this reaction, right? Now we've just mixed in half of an oxygen molecule. This reaction might not happen because we've defined the chemical reaction to happen with oxygen, elemental oxygen, like that. And so so if you guys go farther in chemistry, you'll find that, well, this reaction just represents the net change of species, right? We have a butane molecule here reacting with an oxygen molecule that makes carbon dioxide and water molecules. But the reality is this reaction represents a lot of very, very complicated steps, right? And those are going to be what are called elementary type reactions. And those elementary type reactions involve, well, this butane is going to break into half of a butane and another half of a butane molecule. And then both of those are going to coordinate with maybe the oxygen when it's vibrating at a very specific frequency, and that's represented by an elementary step in the reaction. What we're looking at here is just the overall net result, It's like if we're looking at, the Warriors play the Lakers and they blow them out like they usually do. Then we're looking at the final score of the game. We're not looking at every individual play of this reaction. Right? So yeah, it is interesting to think about, right? And that's what people study is the actual mechanisms for this. These are useful for laboratory settings where we're actually trying to, find relative quantities to actually make something. But yeah, good question.
So you can have that, like, you can have a half, just not when you're balancing?
So when you're doing the calculations, those two ratios, so if you took 13 divided by 10 and 6.5 divided by 5, that would give you the same number, right? So those ratios both work numerically for the convergence. For the balanced chemical reaction, it just doesn't make sense because you can't add in 3.5 butane molecules, right? It doesn't make sense to add 3.5 butane molecules, or like you're filling up your, right? Because this is like a combustion reaction. This is like how you get fuel in your car, right? The combustion reaction. So you can't just put 3.5 butane molecules in your engine tank, right? That doesn't make sense to put in half a butane molecule. It's because we're looking at a symbolic representation of the reaction happening. The real molecules zipping around and stuff like that are more complicated. And you can have half of a butane molecule because you can break a butane molecule in half. But in terms of mixing things together from reactants to get products, it doesn't make sense to add half a molecule. Does that make sense?
Yeah.
Okay.
It's just that I literally just seen today, I seen a chemical reaction.
Yeah,
and
people.
it's like a half.
Yeah, people will do that. They'll put half numbers in there, right? So when you go far enough in chemistry, I don't know why they do that. It's always standard to put full number ratios. Usually when I've seen it, it's when you have other disciplines that are writing chemical reactions. So biologists or physicists that write a chemical reaction, they don't put a whole number, right? Because they're like, well, this is the simplest form I can get it in. But technically you can divide everything by 1,000,000 and get the smallest mole ratio for everything, but it doesn't really help you in any way. But yeah, good question. Okay, all right. So that's kind of where we ended off, right? We ended off with balancing chemical reactions. We had our solutions and concentrations, intermolecular forces, and the stoichiometry, which represents the number of things going in and things coming out of a chemical reaction, right? And we're just kind of counting in fancy ways. So now we're going to talk a little bit more about the specific types of chemical reactions that we're interested in or that are interesting to us. All right, so generally the types or classes of reactions are synthesis or combination reactions, decomposition reactions, single replacement reactions, and double replacement reactions, both of which we've looked at in lab already. Right, that was when we were asked to find the different equations and half reactions, so. And then also we have combustion reactions, and then we have a couple other reactions that are kind of fall under double replacement reactions. So for example, like neutralization reactions, redox reactions, those all usually fall under those categories. Okay, so a synthesis reaction. This is going to be a reaction where we have two elements or compounds that combine to form a larger compound, right? So this would be something that looks like A plus B, then goes to AB, right? You form a larger molecule from either two smaller molecules or two elements, right? So this is what it means to synthesize something, right? We made something new. And this is, in general, a simplification of a lot of processes, right? Because you can synthesize things where you have lots of byproducts and you're still considering that you're synthesizing one specific compound in your chemical reaction. So in this case, we would have iron and sulfur coming together, right? And one thing I'll kind of just introduce right now because it'll be important for redox reactions is that when we have lone elements like this, before they become ionized, we would say that both of them have zero charge on them, right? Once they get close to each other, right? Which one's gonna be the more electronegative element, the sulfur or the iron? Sulfur, right? It's right under oxygen, and oxygen's really electronegative. And we know that metals tend to be positively charged, right, which tells you that they're likely to give up their electron. Electronegative elements like to hold on to their electron, right? And so once they get close, sulfur rips the electrons off of iron, and we get a -2 charge and a +2 charge in our resulting equation here. Okay, so this is just looking at the movement of electrons, which for this reaction, we're not really classifying it as a redox reaction. And we'll talk about what a redox reaction is, but we see that in this case, the iron and the sulfur both go through processes of either oxidation or reduction in this reaction, which is the movement of electrons. Okay, then we have decomposition reactions. So this is where we have a larger molecule that generally spontaneously decomposes to form two elements or a smaller compound, right? So this is where we have the opposite of what we just wrote. Decomposition is the opposite of synthesis. And we have AB is going to go to A plus B, where A and B can be either individual atoms or it can be different molecules or compounds, right? So for example, if we have mercury 2 oxide, that can decompose into 2 mercury metal ions and oxygen gas, right? So if you were to write the balanced chemical equation based off of the molecules here, what would be the balanced chemical equation here? All right, so this is a pictorial representation. This is what our chemical reaction or chemical equations represent, right? This is the actual chemical reaction that's happening. Our chemical equation for this would be 2HgO goes to 2Hg. This will just be solid Hg. You don't have to know that. Plus O2, and we know it's going to be gas. All right, that would be the chemical equation for the chemical reaction that's represented by the pictures there. All right, so this is a decomposition reaction. And this happens a lot. For example, one example of a decomposition reaction is if you have carbonic acid in a soda, right? It can decompose into carbonate ions and hydrogen gas, right? The gas starts bubbling out of the solution, and the carbonate stays as the ionic, an ion in the solution itself, right? So these happen usually spontaneously, right? You put something in something else, it starts dissolving into, right? Especially in water, we see that a lot, right? You put something in, it starts bubbling and dissolving. Hydrogen peroxide, you put in water, right? It'll start making hydrogen and oxygen gas.
Is it kind of
guess
like
so.
when we did the copper and it broke down?
It depends on which step that you're talking about for the copper. The original one, right, that one wouldn't be considered a decomposition reaction because we're actually starting from a pure copper metal, and it's bonding to something to make it aqueous in solution. So you make copper nitrate, which is then aqueous in solution. But then when you make the copper metal again, at that point, that would be considered a decomposition reaction because you're probably starting from, copper phosphate compound or something like that. And then it breaks down into phosphate ions and then pure copper metal. So different steps of that whole copper cycle that we looked at would be considered decomposition or synthesis reactions. Right? Then we have the single replacement reaction, and this is we have a more reactive element replaces a less reactive element in a compound, right? And so these are related to what's called activity series. Right, an activity series, depends on, I'm the biggest fan of activity series, but activity series just represent how likely a compound is going to be reduced or how likely it's going to react. Those are all kind of synonymous with each other. And so in this case, if zinc is a more active metal, right, so zinc is a more active metal than copper, then what happens is when you put them in solution with each other, the zinc is more likely to B with the sulfur, more likely to react with the sulfate ion than the copper metal. So it's going to replace the copper's spot on the ion. And so these are in the general form. If we have A plus BC, we get B plus AC, right? Where A has taken the place of B bonded to C. And this is only true if A is more active than B, right? If A is not as active as B or less active, then no reaction will happen in that case, right? So you require, and really the activity is just, like I said, it's a simplified way of describing reduction, right? Because in this case, zinc starts off, what's the charge of zinc gonna be when it's just in a pure metal like that? It likes to be +2, and it will be +2, but it starts off as 0 here, right? Because any lone atom or any lone pure form of that atom, so fluorine, chlorine, bromine, nitrogen, oxygen, hydrogen, are all in the diatomic form. But everything else, when it's alone like that, is going to be 0, is going to be what the charge is. And then once it bonds to sulfate, does anyone know what the charge of sulfate is? When you're it's -2. It should be -2, right? And it's always going to be -2 because it's a polyatomic ion. So now, what's the charge of zinc for this whole thing to be neutral here? +2. Right, so that's +2. And so really what's happened to zinc in this single replacement is it's been reduced, right? Because reduction is considered what? How do we define reduction?
They gained an electron.
Or sorry, it's oxidized, sorry, not reduced.
Lost it.
Yeah, it lost electrons in this process, right? It lost electrons in this process. And the opposite has happened for copper,
Oh, it neutralized.
right? Copper turned neutral because now it's in its lone elemental form. And it started off as +2 before you mix them together. And so this activity, it's saying, well, zinc is the more active metal, is really also saying that copper is more likely to be reduced. And the reason that it's described that way is because that's actually what we measure, is how likely something is to be reduced. And that's what drives this happening in this reaction. That's why zinc actually replaces the copper, because copper is more likely to be reduced in this reaction. And so again, we'll talk about this more when we talk about redox, but redox reactions kind of happen in all of these different chemical definitions of different chemical reactions we have. The idea with single replacement is just that one metal, is usually metals that we're talking about, is more active than the other metal, so it takes the spot in that ionic compound usually. Right, so zinc is more active than copper, so it takes the spot of copper bonded to the sulfate ion. Okay, and then the more important one, or more common one, I shouldn't say more important, the more common one is going to be the double replacement reaction. And so here we have potassium chloride and silver nitrate mixing together. And you're going to be looking at whether or not they exchange places with each other. And so it's the same idea in terms of one metal being more active or less active than the other one that we just looked at in single replacement reactions, except now there's going to be another ion for the one that was left alone in solution. There's another ion for it to bond to. All right, so this is of the form AB plus CD goes to AD plus BC. All right, so you can write those in any order in just generic alphabet. It doesn't make a whole lot of sense. Usually whatever the cation is, we're gonna do first. So technically, I guess it would be AB, so it goes for AD plus CB is what it would be. I'll write it that way just because we usually write the cation first, and this is the cation in both cases. Right, so both of the anions have exchanged the cations that were present. And this again is usually ionic exchange, but there can be other things like when we saw the sulfuric acid a little bit ago with aluminum hydroxide, that sulfuric acid donates single protons and then water gets involved and it can be a little bit more complicated. But the idea is still the same, right? You're exchanging cations with the two anions that are present in solution. Okay. All right, so let's go ahead and continue. All right, so these are double replacement reactions. And so the last one we were going to talk about was a combustion reaction, which is the one we've talked about balancing a lot. This is any reaction where you take some sort of organic molecule, react it with oxygen to then make carbon dioxide and water. Right, so these are always going to be the general form. For combustion reactions, the only thing that really changes in a combustion reaction is the organic molecule. When I say organic, that usually just means that it's a carbon-based molecule. Right, so this is a carbon-based molecule, and this is the only thing that will change from different combustion reactions. And how this is used. An engine, for example, right, is you combust, you ignite some fuel, it expands, creates carbon dioxide gas and water vapor. It can create, and then causes a piston to move, for example, right? Causes a piston to expand, and that's what drives a mechanical engine. And so it says it also produces a large amount of heat. As a result, this is a very exothermic reaction, right? Which means that heat is represented on what side of this reaction? The product side, right? So because it's exothermic, it means that we've released a lot of heat from this reaction. And just take a second to review what exo and endothermic means, right? And how we can look at our energy diagrams for what a exo or endothermic process is. All right, is anyone still writing on this or writing this slide right now? Okay, I'll give you guys a second. Right, so an exothermic was something that releases energy or releases heat. What does an endothermic reaction do? It absorbs it, right? It requires that from the surroundings for the reaction to proceed. That doesn't mean that you don't have to put any, right? So, because if you just have a bunch of methane or a bunch of octane, which is fuel, you just have a bunch of octane lying around, it doesn't blow up, right? What does it require? Right, how would you get it to blow up? Yeah, you'd add a spark to it, right? You need some little bit of energy to kind of kickstart the reaction. But once it happens, then it all blows up, right? Then the chain reaction happens. But you need that little bit of energy to kickstart the reaction. And so, again, if we had endothermic versus exothermic reactions, in endothermic, I'm going to draw both of the plots. Right, this is our reaction coordinate, which is the same thing as just saying the reaction progress. Coordinate. All right, if our reactants start off at some energy in endothermic reaction, where do the products end up? Higher or lower? Higher, right? Because we've taken in this amount of heat, right? This is delta H, which is the heat of the reaction. We required this amount of heat to reach our products. And then if we have an exothermic reaction, where do the products go? Above or below? Below, right? Because the energy of our products is below, which means that we've had to get rid of some energy. The actual value of the energy is lower, which means that that energy is gone somewhere. And usually that's in the form of heat in the reaction itself. This right here is called the transition state. And the difference between that and where you started, does anyone remember what that's called? Yeah, it's the activation energy. EA is our activation energy. In our example of lighting the fuel, what does the activation energy represent? Or getting the fuel to explode. What does the activation energy represent in that process?
like the moment the heat reacts with
In a way, yeah. So in a way, it is the moment the heat kind of interacts with the system. It's when we ignite the spark, right? It's a little kick of energy that we have to give to the system for the reaction to actually proceed, right? So even for an exothermic reaction, we still have to add a little bit of energy to get it to happen, right? That's why we have to add a spark or add a flame to the fuel to get it to ignite. It doesn't just happen automatically. That activation energy represents how much energy that we have to add. So either it's a spark or putting a flame to the gas or something like that, right? And so in each of these cases, these were the reactants, and this was the products. All right, so these were our energy diagrams for endothermic and exothermic reaction. Vanessa?
I have some like corny way of remembering.
All right, we love those, so.
So for endothermic, I kind of said like tengo frio, like in Spanish, like tengo frio,
Uh-huh.
because it's cold, so you need
Uh-huh.
to absorb heat.
Mm-hmm.
And then for exothermic, I don't know if anybody listens to The Weeknd,
I,
but his thing is like XO,
uh-huh.
and so I kind of think of it like fire and that's kind of like my silly way of
Yeah, I like that. So it's definitely some layers to that one, but I, I like it, right? XO is fire, right? And then usually, even if you don't, find a deep connection with either endo or exo in that case, if you just remember, oh, XO, fire, the weekend, right? Then at least you know the other one is just the opposite of that, right? So if you at least can relate to one of those, then you'll be able to remember the opposite just by, okay, well, if I remember this one, then I know automatically what the other one is. All right, yeah. So thank you for sharing that, Vanessa. So hopefully, that'll help you guys remember that. Right. So I the Tango Frio one, I'd have to think about a little bit more. But it makes sense, right? If it's cold, right, endothermic processes take in energy from the surroundings. So when you touch them, they're cold, right? That's why when you sweat, you cool down because it's an endothermic process. As the process happens, it takes heat away from you, right? Oh, and also Tango Frio. You dance, you sweat, you release heat. It's endothermic process.
and EXO is releasing, right?
Exo is releasing, right? So it's like the weekend's fire, and his thing is exo. I don't know the exo thing though. What is that?
It's his label, I think.
Oh, like that. It's not like okay. It's just he's associated with it.
Yeah.
Okay, kind of like exo, something like that. Right. So that's fire release energy, exothermic process. Right. So that works. All right. I'm trying to think if I have any. I don't know if I have any good ones. They're probably just boring chemistry ways to remember that.
Well, EXO kind of sounds like exit.
Mm-hmm.
Think of something
Heat's
else.
exiting the system. Oh, I like that. Yeah, exo is like heat is exiting the system.
And endo sounds like in.
Entrance, so heat's entering the system. Oh, that's a good one. I like that.
I think,
Hmm.
I think endo, like endodontist,
Uh huh.
like they work inside the tooth. the
Uh huh.
inside,
Yeah. Uh huh.
And then,
All right. Yes. This is bring.
endocrinologist inside also.
Uh-huh. Okay, that makes sense. Yeah, so it's taking something inside, right? So that's related to, I know a lot of people here are planning to go on to health sciences and stuff, so that works too. Endo is inside, right? So it's taking the heat inside for the process to happen. Oh, I like that. All right, thank you guys for sharing. I should do that more often. Anyone else have any other good ones? All right, so now I'm really going to be expecting you guys to remember endo versus exothermic, right? You got a lot of ways to remember this. Okay, so that for combustion reactions, those are very exothermic processes. Okay, so how would we classify each of these reactions before, right? So this is a good multiple choice question for the final. Like, how would you classify each of the following reactions? So for the first one, how would you guys classify that?
That is a single.
Mm-hmm.
Oh, yeah, single placement.
This would be a single replacement, right? If this is our Cl2 is kind of like our anion here, right? Where the magnesium is replacing, right? So this would be like A, this would be B and C. Then we have AC plus B. This would be, yeah, it's replacing the copper, right? Which means that the magnesium is what compared to, it's a more active metal than the copper. What about the second one?
Decomposition.
Yeah, so this is like the type of reaction in soda that I was just talking about, right? You have calcium carbonate, you put it in water, you're gonna get calcium oxide and CO2, and CO2 is a what? What state of matter is CO2 usually? A gas, right? So, right, if it's not a gas, usually, you don't see it in liquid form that often. Where else do you guys see CO2 if it's not in gas?
You don't see it, but.
You can see it if you compress it a little bit, if you compress it really hard. And it's not that uncommon. You guys, and I know you guys have all done something with it before. Maybe made ice cream.
Like that.
It's the dry ice, right? So compressed CO2 is dry ice, right? So you can also see it in solid, but usually it's gonna be in the gas form, right? So this is a decomposition reaction. Second, my eraser is not working. This is decomposition because we're taking something that's a larger molecule and decomposing it into two different. And usually the types of reactions you see this for are gas forming reactions, right? So, and precipitation, you see this for a lot too. Okay, what about the next one? This is a double replacement. This is a weird one. Usually if you see water as a byproduct too, it'll show up like this, where we have a hydroxide and then two hydrogens here and then calcium. So this would be like A, B, C, D, and now the calcium takes the place of the hydrogen bonding to the chlorine, right? So now we have C, B right there, and then the water, the hydrogen, and the oxygen start bonding together. And so it's a little harder to identify because we don't have hydroxide ions in solution anymore, but the hydroxide ions and hydrogen have come together to form water molecules, right? So this is, it's weird to look at, but this is the A, D, right? And I'll put a little star there just because it's hard to realize that. But this is a double replacement. Do you have a question, Summer?
Is that also considered a neutralization?
Yeah, this one would also be considered neutralization.
Water, right?
Yeah, water is always I'm going to write this better because that's really fat. But yeah, when we'll talk about neutralization in a second, and in lab today, we're going to be looking at neutralization reactions. Double replacement, right? So there's a couple different ways, right? Double replacement is the highest level of what you would say this type of reaction is, but you can get more specific from there, right? So for example, if you're given this question as free response, both of those would be acceptable answers, but if it's multiple choice and you see double replacement there and there's no neutralization, then that's how you would classify it. Or vice versa, if double replacement wasn't there but neutralization was there, then you would see that. And neutralization also has, calcium hydroxide and hydrochloric acid is an acid and a base mixing together, which is also why that's considered neutralization. But we'll talk more about that in a second. And what about number 4? What is that? Synthesis, right? So this is a synthesis reaction, right? So A plus B goes to AB. This is going to be a synthesis reaction. All right, any questions on any of those? All right, so the hard ones here are sometimes neutralization reactions to identify because the hydroxides and the hydrogens formed water when they come together. Okay. And so some of this is what I was saying, the subcategories for specifically double replacement reactions that you may see is we can have precipitation, so that's the formation of a solid, right? Precipitation can happen, for example, if you have lead metal in solution and chlorine gas, and you get lead chloride. Or neutralization, formation of water. This is why it's called neutralization. It's an acid plus a base equals water plus a salt is what we get for neutralization. And then unstable product, this is like the decomposition of carbonic acid into carbon dioxide and carbonate ions in solution. All right, so this was like the, it's unstable because we have the spontaneous formation of gas. When I say spontaneous, that doesn't mean that it's spontaneous all the time, just under certain conditions. And right, so this goes into the field of thermodynamics, which we're not really going to touch on much in this class. But for example, if you think about soda cans, right, when they're in the can, usually they have a very high pressure in there that keeps that carbonic acid stable inside of the soda. But as soon as you open it up to the atmosphere, the pressure reduces And now no longer the carbonic acid is no longer stable inside the solution, right? The pressure has changed, and then you get the unstable product at that pressure, right? So carbonic acid at low pressure would be unstable, and then at high pressure it's stable in solution. And then that's why you get the formation of gas. Vanessa?
That says acid plus base.
Yeah, acid plus base. So usually neutralization reactions, how you do that, you mix an acid with a base, and then you get water as a byproduct, right? So you don't change the acidity or basicity of the solution, and then you get salt as a byproduct. So precipitation reactions, again, this is a double replacement reaction, right? Because here we have potassium and a chromate ion, and then barium nitrate, right? That's how we would identify A, B, C, and D here. And the barium takes the place of the potassium. We get barium chromate. So this is going to be CB plus AD, right? So that's how we classify it, as a double replacement reaction. We replace the ions. The reason that it's called a precipitation reaction is because we get a solid product here, right? So the solid product, where we started off with aqueous reactants, right? So we start off something that's a solution, right? We don't, it just, maybe it's colored solution, maybe it's clear, but it's a solution, right? So there's these ions and these ionic compounds are dissolved in solution. As soon as we mix these two solutions together, though, we get the formation of a solid product, right? And the formation of that solid is what we define as precipitation, right? So in the abbreviation for precipitation is just PPT, right? So the formation of solid defines precipitation. Right, that's why we call it a precipitation reaction. And how likely this is to happen, you know, depends on a lot of things you have in solution and inherent properties of the material. So for example, if barium was a lot more active than the potassium here, then that would make the precipitation very likely. If it's about the same activity, then maybe only a little bit precipitates. So the amount depends on properties like that as well. And it also depends on properties of this solid as well. If, for example, the solid doesn't like to be in water, right? It doesn't like to be in the aqueous phase, like it's not happy surrounded by water molecules, so it crashes out. And if you have a lot of water, it's gonna make this harder to dissolve in there, which makes, it's gonna make that reaction harder to happen. All right, so that's precipitation reaction. Any questions about it?
Is there a way that without actually physically seeing it, that you would know if something, like what form it is in, like solid, aqueous, gas, or?
So you're saying, is there a way without observing it,
Yes.
how you would know that this is going to be solid?
Yes.
You would know based off of properties of that material itself. So you'd have to understand it at some level, whether or not that likes to be in the aqueous phase in water or not. And so that just depends on the solid. You could probably calculate it from, you know, very complicated quantum mechanical equations, but knowing it just by saying, oh, I'm gonna mix these, a lot of these things are determined just because people mix stuff together and then say, hey, this precipitates. And then they can measure stuff that confirmed that, right? Mm-hmm. Vanessa?
So in a test, would you ask us to identify like double replacement and any of the three sub?
I could, you know, it wouldn't necessarily, I probably wouldn't ask you both at the same time. But for example, if I said, you know, what type of reaction is this? And I had single replacement, you know, combustion, neutralization, precipitation reaction, right? Out of those four, you know that this would be the most accurate description. I wouldn't put something like double replacement and then precipitation right next to each other. This is more, you know, it either would be part of a much larger problem, you know, very small, you know, like, oh, what is the name of this compound type thing, or a multiple choice type question, identifying the types of reactions. Yeah. Mm-hmm. Okay. So the neutralization reaction, again, this is more some important reaction for acids and bases because this is how, for example, buffers in your blood work, right? So in your blood, you have molecules, it's a phosphate buffer that can act as both an acid and a base. And what it does is whenever you drink a lot of lemon juice, or maybe you swallowed some bleach you weren't supposed to, it works to reduce the change in pH of your blood, right? You want a very specific pH for your blood because all of your biological processes, metabolism, synthesis of RNA, proteins, DNA, all those things require the pH of the solution to stay the same. And even other things like the proteins that make up your eyeballs and stuff like that, they have a very specific shape. If you change the pH of all these solutions they're in, charges on the protein change, all of a sudden things start unfolding and going weird ways that causes, catastrophic. Right, so the buffer in your blood works to resist that change in pH, which means that it can neutralize, right? Neutralization reaction is the type of reaction we're looking at, whatever's coming into your blood, right? So for example, if you had something like what we had before, we had an acid, and let's say there was a base there present in solution, the byproduct is always going to be water. So we're always going to have water as a byproduct because it's not letting the pH of the system change. It's just basically going to give you water. And then you'll have a salt. So in this case, your salt would be sodium ions and chlorine ions. And generally, depending on the type of salt, they'll stay aqueous in solution, right? If we have chlorine, that's where chlorine comes from. Should I use the laser pointer? Right, chlorine comes from your hydrochloric acid. Sodium comes from your sodium hydroxide, right? And that's where you get sodium and chlorine. If, you could also write it as NaCl, aqueous, but the reason I don't put that there is because what happens to salt when you put it in water? It dissolves, right? So it splits up into the ions. So technically, you get the ionic forms of both when you put them in, but the byproduct is salt overall, right? We just have some floating ions in solution. And so this is for when you mix specifically an acid or a base together. For a buffer, right, what a buffer is if we have a generic acid, HA, it can go between its two forms, right? We have acid on the left, and then it can also act as a base, right, on the right. That's A minus is what we say is the base. When it loses its proton, it stays as A minus. And so if we add acid, so I'm not going to expect you guys to know this. This is just to make it a little bit more relevant to real life. If you add acid to your buffer system, your A minus is going to come in, HCl, and it's going to become HA, and the byproduct is going to be water in that case. If we add sodium hydroxide, and you get a chlorine ion here as well. If you have a sodium hydroxide and you have the acid component of your buffer, right, since it can switch between both of those, it's going to then react with the hydroxide there, and it's going to make A minus and water plus whatever ion you have left over from the acid. And so you may be thinking, well, where's the water coming from, especially in the acid equation? Because, you have H2O, there's no oxygens involved in there. That's because of stuff we'll talk about more when we explicitly talk about acids and bases. But for a strong acid, when you add it to water, it goes to the Cl minus plus H3O plus. And what we're going to learn is this H3O plus is very important for how we define how acidic or basic a solution is. And the base is the opposite. When you add base to solution, you get OH minus, right? And then the proton from the hydrogen atom from the HA goes to the OH minus to make water. So the reason that, we get a water here when I don't have any oxygens on this side is because it's assumed when you add this to water, this whole thing happens. And so really it's like you have this on the reactant side there. So you lose the Cl, the A minus takes one of the hydrogens from this, right? So I know there's a lot of arrows going on. And then that's what generates the water. If you remove one hydrogen from H3O, you get water. Like I said, this is just to identify a neutralization reaction. We'll talk much more about acids and bases in the next 2 weeks, right? And so, but that's just how the buffer in your blood works, right? The HA and A minus, that's the buffer in your blood, and it can absorb and neutralize base and added acid to the solution. So that's why it's a very important reaction. It's also an extremely exothermic reaction, which means if you mixed acid and base together in the lab, what do you think would happen if you were holding the glass? It wouldn't blow up, but it'd get very hot, right? So it'd get very hot. So when you guys did that, when one of your Petri dishes a couple of weeks ago, if you were feeling the actual well plate, it got warm when you put the acid and base together. That's because it's very exothermic, which is why you don't want to store acids and bases together, because if there's an earthquake, they spill. That can cause a fire if they're very concentrated. But the fact that it's also exothermic means that it's very likely to happen, which is what you want, because if you add acid to your blood, you don't want it to only react with some of the acid. You want it to react with all of it. Okay, so that's a neutralization reaction. That's what we're going to be talking about more today. And then we have the last one, which is unstable product reactions. And so this is reactions that are usually going to produce gaseous byproducts, right? Because for example, in soda, this was the carbonic acid that releases CO2 gas. It's not stable at low pressures, which is why when you open it to the atmosphere, the soda bubbles. Or you have sulfurous acid, and so that one in certain conditions, so at high temperature, it's not stable. And that one you just don't want to be around when that starts bubbling that, because it'll make a nice little brown gas that's coming off, and it smells like sulfur smells, so like rotten eggs. All right, so these are unstable product reactions, which are decomposition reactions in this case, right? So usually a decomposition is when something is not stable, right? So decomposition, usually when the reactant isn't stable. And so generally, when you have something that's not stable, in overall chemical equations, you don't really include them in there. So when Kai asked earlier about what if you added half a molecule and stuff, that might be part of the process, but because all those intermediates, all of the elementary reactions that are going on, you don't directly observe them as the end before and after, right? Because they only exist for a very short time and then they disappear, right? So if something is unstable, it only exists for a little bit and then it disappears. So if you have something that's unstable in a chemical reaction, generally what you do is you replace it, right? So here, this would be a double replacement reaction, right? We have AB plus CD goes to CB plus AD, like this is a double replacement reaction, but technically this compound right here isn't stable, right? So it's only very short-lived. As the reaction happens, you're using up all your carbonic acid. It's decomposing into its, carbon dioxide and byproduct of water in that case. All right, so whenever you have a decomposition reaction, the net reaction should only have stable molecules. Go ahead.
So would you actually want to write that as like H2O and CO2? Or
Yeah, so this is what happens, right? And if you notice the net reaction, right, this decomposes into CO2 and water. Right, and this isn't something that I would ever expect you to know beforehand, that, carbonic acid is unstable and it would decompose and exactly what it would decompose to. But if I gave you a chemical reaction, I said, well, there's a lot of gas forming, and one of these was unstable, for example, for, there's a lot of gas forming, would you expect the reaction to be stable or unstable, or one of the products to be stable or unstable? How would that affect the overall net chemical equation, right? So this is the net reaction, or the net chemical equation. And the important part with that is just that the net chemical reaction or net chemical equation just doesn't involve stuff that's only there for a short period of time, right? If it's not stable, then we don't include it in our reaction.
But you can tell by like the ratio of the numbers, right? Like how there's two of the hydrogens and.
Yeah, you would be able to tell. It's just, for example, carbonic acid we just talked about, so you know that it goes into carbon dioxide. But if I gave you phosphoric acid or something, you're like, wait, I don't know exactly how that would decompose. And you can have more complicated decompositions too. But yeah, maybe for carbonic acid, it'd be easy to say, okay, what does this decompose into if carbon dioxide is one of the products? Then you'd be able to just know from stoichiometry that water has to be the other one. Vanessa?
So, earlier when you were talking about like decomposition.
Mm-hmm. Yeah.
So not every decomposition chemical reaction is unstable, but every unstable, like the unstable
Mhm.
decomposition reaction does need decomposition.
Is some sort of decomposition. Yeah, if it's unstable, then it's always going to be some sort of decomposition because whatever product you're looking at isn't, by its very nature, it's going to turn into something else because it's not happy being in that state. Yeah. Did I answer that? I don't know if I mixed it up.
No, I got it.
Okay, all right. All right, so let's end there for